Welcome everyone. So this is our 77th live stream geometry. We have two people here with us so far. And today I'm going to go through some problems on the Art of Problem Solving forum that were sent to me by Serdar. So one of the two people on the session currently. So they look pretty interesting. And if you'd like to join us in the future, feel free to email me at mgreenb801@gmail.com. It's going to be in the description of my video, and we meet every Sunday at 8 a.m. US Central Time. So I know the IMO just finished this week, so I'm still working through a lot of those problems. I solved G4 recently, which is really fun. That's actually not from the IMO. That's from the IMO shortlist from last year, which they just released. So if any of you want to try it, I would definitely recommend it. All right, so I'm going to share my screen. Hold on just 1 second. Okay, so this will be the first problem. So this is posted on AOPS by the user Thinking and Doing. So we have a triangle, we have a triangle ABC within circle I. And it touches BC at D, and then we draw the perpendicular bisect. Oh, whoops, this should have been I. And this should be B. I'm going to go close this. Then we draw the perpendicular bisector of DI. And we see, oh, whoops, that's just the perpendicular line. We want the perpendicular bisector. This looks a little bit familiar, but I've done so many problems on my channel that I feel like everything looks a little bit familiar. Let's draw IB. Okay. At M. All right, so IM intersects BC at N. NE intersects is tangent at E. Okay, so basically we draw the tangent from N to the circle, or to the incircle. That's tangent at E. And we want to show AEMN is cyclic. This is an interesting configuration. Let me hide some of the excess. All right. That is tangent. And we have a perpendicular bisector. So let me draw the midpoint of IB. And this is a perpendicular bisector. All right. AEMN. I wonder if that's
IMD and AND are similar triangles.
Sorry,
Triangle.
IMD and
END.
END. That's interesting. Yeah, we know they're both isosceles. And is it obvious that MDN is isosceles? Let's see.
Yeah, they are similar.
Okay.
But is it
Yeah.
obvious that they are similar?
Let's see. Yeah, it's true because basically we know triangle IDN is a right triangle, and we know M is the midpoint of IN since this is a perpendicular bisector. So basically MI equals MD equals MN. And so this angle is this angle is this angle. And then, yeah, it's not, yeah, they're similar.
Can you intersect AE with circle?
Yeah. I guess on both sides or just up here?
AE.
Oh, AE, okay.
Can you check that if GF and what was the other point I cannot see? GF and IM, if they intersect on the circle.
Yes. No. Let me draw AEG again. I was thinking about using the power ratio lemma because we know we have one circle that passes through A and M, right? We could find another circle, then yeah, maybe we could use the power ratio lemma. Let's see. So what strategies can we use? So
Can you check that if M is the center of AGN?
AGN, okay. Oh, sorry about that. AGN?
AGN. If M is the center of AGN.
So, sorry.
It's in center.
Oh, the in center. Sorry, I thought you were saying the center. Okay. Yes, just a second.
Because AM must be angle bisector in angle EAN.
Okay, so it looks like I see what you're saying. Okay, so it looks like it's true.
We know this must be true, but I'm not sure the others.
Oh no, AGN, it doesn't look like it. Yeah, like you can kind of tell from that picture, Yeah. But we know AM is an angle bisector. That's what you were saying, right?
We want it to be true.
How do we know that AM is an angle bisector here?
We don't know, but we want to prove it.
Okay. Okay, so we want to show like angle GEN equals angle EMI. But EMI equals angle DMI.
What if we invert around the circumcircle of EIDM?
Okay, so I'm going to draw that circle.
M is its center.
Okay, yeah, M is the center of it. Okay, so let's see what we can invert. So where would it, we want to see where AE, so a circle passing through the center of inversion. So N stays at N. N and E remain fixed. Let's see where A goes. Okay, basically we want to show that the inverse of A lies on EN, right? That would solve it, right?
Yeah.
Can you draw the perpendicular bisector of ID and intersect it with
Yeah.
circle again?
Yes. The circle, right?
It looks
Yeah.
like the inversion of circumcircle is tangent to the incircle.
Oh, really?
Yeah.
Huh. Well, because the circumcircle passes through the center of the circle, so it's going to invert to a line. Interesting. Oops, sorry.
Can you intersect AH with IM?
Yeah.
we prove that GM and HLM are similar, then we are done.
HLM and EGM. Okay.
It helps us to get rid of. Actually, I'm not that sure.
Oh, this circle?
If this is helpful, I'm not sure if this is helpful.
Okay. Let's see, HLM and AGM. Yeah, we know that one angle is the same. So yeah, showing the bisector would solve the problem basically. Let's see. And we just need to, we need to show AM bisects EAN. Let's see. There's some way we can use the angle bisector theorem. So AGM is similar to HLM. We want to show that. I don't know if it helps to draw this point and try to show MO equals MG. We call it P. Yeah, what can we say about AEG? So DE is the polar of N. would be similar triangles. I wonder, what can we say about J and K? Are A, I, and K collinear? Let's see. No. Let me try something. I wonder if AJ and AK are isogonal. Oh, that would be obvious. Yeah, that AJ and AK are isogonal because M is the midpoint of arc JK. So, yeah.
Oh, I know how to prove that JK is tangent.
Oh, yeah?
Yeah, it is actually not anything specific to point M. That would be true for any point on circumcircle.
Okay.
That is, we would use that Ponslet porism. I think that is it is called. So,
really?
like, you take the tangents from M to the incircle.
Okay.
And let it cut the circumcircle.
Let me do that. So yeah, so this is going to be tangent to the incircle by Ponslet's porism, right?
Yeah, and now you can see actually that this is a kind of known problem because we just have an incircle and the circumcircle, like the circle with center M and which passes through I.
Mm-hmm.
And that is a problem I have seen before. I think it has a solution with inversion. So, like, you invert around this circle with center M, and the circle goes to some, like, the mixed linear circle or something like that.
So I invert this circle around this.
Yeah.
Oh yeah, and it's like tangent. Interesting.
It is some Peru problem, I think, from some TST.
Okay. But then that would eventually prove that this is tangent to the incircle. Yeah. Okay. All right, I'm just going to assume that's true for now and see what that gets. Yeah. So yeah, we want to show this is an angle bisector. I wonder if there's some other circle we can use for that. Let's see. AE. Yeah, maybe there's like a circle. AED. Yeah, I don't know. Yeah, it's really point E is kind of hard to use. That's the thing. So ED is the polar of N. I wonder if there's some other, yeah, I don't know. How do we use point E? Let me draw the center of ABC. It looks parallel, but I don't think it actually is. There's no way. Yeah. Wait a second. So let's say I draw this segment. Then I draw, so you know M is the midpoint of arc JK, right? So if I draw this and this, then we know that angle MJA prime is equal to angle MAJ. So that would show that MA prime times MA is MJ squared. Wait, did I just solve the problem? I don't think it should be that easy.
Yeah, it looks really easy.
Actually, we know M is the midpoint, so isn't it obvious? MA prime times MA equals to MJ squared.
Yeah, so let's
But I think you have assumed that A prime lies on JK. which is what we need to prove actually.
Yeah, so what if, I guess, what if I call this like R? Then we know that MR times MA is MJ squared, right? So I let R be the intersection of AM. Oh, but then I'm assuming that these concur, I guess. That's the problem. So yeah, it's because I'm assuming, I mean, basically I'm assuming JR and K are collinear. One sec, I'll be right back. All right, thanks for waiting. Let me finish this one up. Yeah, if we show R lies on the radical axis, then it would be trivial by power of a point. So yeah. So yeah, maybe it's best to define R, sorry, like this way. Because then we know Q lies on the radical axis. Yeah. wait a sec. Maybe there's so if we define this point right here, where AE intersects BC, then I think we want to show that AMSD is cyclic, right? Let me draw that one more time. AMSD.
Actually, we can get rid of E. If
We
we
can get-
prove that, can you intersect MI with circle?
Yes. I think I might have already done it, actually. Let me see. Oh no, I don't think I did yet. Okay. Point T.
If we show that TP is parallel to BC, and then we can define E as intersection of in circle with the circle, with the circumcircle of AMN, then it will follow that and E is tangent to in circle, and the angle condition will be hold.
Okay, so you're saying first we show that TP is parallel to BC. That's the first
Yeah.
step, right?
Then we
And
have,
and then then how does it work from there?
we define E as intersection of in circle with the circumcircle of A and M.
Okay, so we
After,
define it
after
that
we
way.
prove, yeah, after we prove parallelity, we will have that A and M equals to MAN.
Okay.
So we will have,
How do we know that
Oh, good point.
AMN intersects the in circle?
that's a good question.
Right.
Yeah,
You just
I-
assume it for now.
yeah.
But, it looks true. Yeah.
Well, it is true, obviously.
But yeah, we
you
can't
can't
prove it.
assume it.
Yeah, we can't assume it. Yeah. Okay, let's see. Can we show that PT is parallel? So angle PTM.
Because the angle MBC is less than MDC. So we will have EAM equals to ENM, which is larger than CAM. So it intersects.
So you know they intersect.
Also, I saw now that you don't need to make that phantom point. Angle trace should be sufficient to prove that it is cyclic after we prove that TP is parallel.
Okay, I don't need which point? This point?
No, what Serdar said to make phantom point E
Oh, okay.
as the intersection of AMN.
Okay. So once we show this parallelism, we're good. Do I need this circle anymore, or could I just hide it? Yeah, for now I think I'm gonna hide these points. See, angle MAP equals angle MTP, which is angle IMF, which is ENM, which is NEM. Oh, that's nice. So yeah, okay. So I'll keep this circle just because yeah. It helps show that angle ENM is MEN. Yeah, that's a good way to do it once we show it's parallel. I'm gonna go hide this for now. All right, so we want to show they're parallel. Maybe you could show like the distance from P to BC is the distance from T to BC. I'm not exactly sure how we would do that, but oops, sorry.
Maybe we can do something with root BC inversion.
Root BC inversion.
Maybe.
Okay.
Since n should then invert to t.
Okay. Yeah, we could try to show some things are orthogonal somehow. Yeah, it seems like a much easier problem to show that TP is parallel to BC. I'm just not sure right now, how to do it. So yeah, maybe we could like, so we have NM times NT is NC times NB, and let's try this out for a little bit longer. I think we're close. Yeah, I'd like to try to show AT, AH, AM, and AP are like isogonal. I don't know if I could use like the isogonal line lemma somehow or something like that. So AT, AL, AM, AN. We want to show like those are isogonal. That would solve the problem. TLMN. Is there any trick we could use? Okay. Yeah, I wanted to use the isogonal line lemma, but I don't see an obvious way. We know that MN passes through I, so maybe that would help. Maybe it's worth drawing a T and letting it intersect EC. So we want to show yeah, I feel like I want to use isogonal conjugates. Let's see. 6.05. Yeah, can we use isogonal conjugates somehow to show? I don't know, maybe L and M are isogonal conjugates here. No. All right, you guys want to move on to the next problem? Come back to this later. What do you guys think?
Not yet.
Okay.
I have an idea with cross ratios.
Okay.
So we can consider cross ratio BC-TP.
Okay.
And we can project onto BC through T.
Okay.
And we will get a tangent at T to the circle, which intersects BC. So, and P should go to the infinity. Oh, that concurs. I didn't see that.
Yeah.
If
Let me
that
make
concurs,
sure.
if we can prove that, that is for sure useful.
Let's see.
And
Yeah,
so
looks good.
we basically want to prove that those two cross ratios are same when you take P to the infinity.
Okay, so tell me the two again. Did you say, so say them one more time?
Cross ratio BC TP.
Okay, so that's like we want to show it's an isosceles trapezoid, right?
Yeah. And when we project, P should go to the infinity, but we don't know that yet. So if we would prove that UB over UC is that cross ratio, then it would be done.
Okay. Interesting. So yeah, UT is tangent to this circle, UD is tangent to the end circle. So yeah, if this were tangent, we have UB times UC is UT squared. And then UD squared is the power with respect to the end circle. Yeah, this looks like a harmonic quadrilateral or something, but I'm not sure. I wonder if there's something special about this point. Oh, are EI and V collinear? That would be weird. Okay, that's not true. I was gonna say, I would be very surprised about that. But yeah, I guess with the idea you had, I'm just wondering, like, yeah, how would we get UB over UC? And also, how would we get the cross ratio of that, like, trapezoid? All right. Oops.
Can we prove that cross ratio BCAM is equal to BCTP?
That's interesting. BCAM equals BCTP.
Yeah, I mean, that would be true if we knew that H lies on AU by
Okay.
projection.
Let me think about that. What if I draw AM? See. Let's see. Yeah, there's got to be some trick to this. We're just not saying right. Yeah, you show TP's parallel. Like some ratios. Let me hide TP for the time being because I keep assuming that it's parallel in my head. So yeah, how would you show that? Yeah, let's move on to the next one. I agree. So let's see. This one, we have the in circle, the X circle. Let me just check through. Yeah, I want to do an easy one for now. This one looked kind of interesting. Let's try this one. I don't know if you guys might have already done this, but this is from, this one has a 60-degree angle. So I'm going to draw a 60-degree angle this way. Oh, I don't know if he proposed it or he got it from somewhere else. Sir, but it's not yours. Do you remember what the source was? On a marathon. Okay. All right. So let's try this one. This one looked interesting. Call this X. Okay, so we have a triangle ABC. Angle A is 60 degrees. All right. AD is the bisector. And then we draw an equilateral triangle where AD is the altitude. So here's what I'm going to do. Let me first take the whole line. I'm going to try to rotate it 30 degrees left and 30 degrees right. Actually, I could just do this. All right, so PDQ, P is on the same side of D as C. So that's P, this is Q. All right. And then we let PB and QC meet at K. And we want to show that AK is this median. So I'll just let M be the midpoint here. There's a couple ways we could do this. Maybe it's also worth drawing a circumcircle of ABC. So AD is a height in that equilateral triangle. Let's just check that the problem is true. B, A, K, and M, A, C.
You named the intersection of QD with AB and ED with AC.
Yeah. Looks a little like Pappus or something, right? Are those collinear by Yeah, by Pappus.
Yeah.
And it looks, is that a rhombus?
Yeah, it is.
It's a rhombus. Okay. So yeah, how do we know that that's a rhombus? Is it obvious?
Angle ADF
Yeah.
is 30 degrees, and
Yeah, I got it. Like right as you're about to say it. Yeah, this is 30 and this is 30. So yeah, it has to be a rhombus. All right.
looks like A is the like the center of cyclic quadrilateral PQEF.
Oh yeah, because yeah, AQ equals AE equals AF equals AP. So it has to be. Yeah, this whole thing is like 4 equilateral triangles.
Can you intersect QB with PC?
Yes. So I wonder if they're parallel.
They must be parallel.
Oh, by Desargues, right?
If we prove that, we are done.
If we can prove they're parallel, we're done.
Yeah.
Let's see. I think it might just be Desargues. Let me think about this. Maybe not. But I don't think they're.
Actually, I guess we don't need. They are parallel. By Desargues, QEB and PFC are the perspective.
Okay, so yeah, QEB and PFC are perspective. And so that means PQE. Does that prove that they're parallel?
I'm not sure. Let me think.
Okay.
I guess this is not helpful.
Yeah, I think are both of these parallel to DA? Because I think this arg says that these 3 are concurrent, right? So yeah, if we can show BQ is parallel to AB, let me see. I'm not sure these.
Cannot be concurrent.
Yeah. Are the okay? They're not all 3 parallel.
If we prove that QB is parallel to BC, then BC AM is parallel to both of them. Then we are done by isogonal line lemma.
Okay. So you think AM is parallel to both PC and BQ, or it would have to be if the problem were true?
It has to be, yeah.
Sorry. Okay, let me think about the SARs again. So Q, C, B, P, and EF concur. So QB and PC intersect at a point. And then, yeah, I'm trying to think what the SARs means. It feels like it means that A, D, and like a point at infinity. Yeah, I don't know.
I've solved it. There's
Okay.
little computation. We will prove that. We know that PQ is parallel to EF. So we can write that BK over KP equals to BE over EA, and QK over KC equals to AF over FC.
Okay.
So we want to prove that FC times BE equals to AE squared. We know that AD equals to square root of 3 times AE, and we know AD, how to calculate AD.
Okay.
So we calculate AD, and by this we calculate AE, and it becomes true.
Okay.
I will write the computations to Discord.
Okay. All right. So yeah, so we have some similar we have CF over FA, the CK over KQ, and then we have the same thing there. So where do you, I guess, where do you end up showing that AK is the median?
We use isogonal line lemma on AQ, AB, AC, AP.
Okay. PAC. Okay, so use the isogonal line lemma. And then, so that means that AK and you'd have to see where BQ and CP. Okay, so, all right. Okay, so if we can show basically, if we can show that BQ and CP are parallel to AM, that solves it. And is that kind of what you were trying to do?
If we prove that BQ and PC are parallel, then it's obvious that AM is parallel to these two lines because it's medial line.
Oh yeah, good point. Hey, John, thanks for joining. So yeah, we're on the second problem. The first one, we made a lot of progress, but we didn't solve it. Okay, so, and these are parallel. So is that what you're trying to prove with ratios, that these are parallel?
Yeah.
Okay. And so how, yeah, so just for Urjan, here's the first one. Someone just posted it on AOPS and Serdar sent it to me. So yeah, you can take a screenshot of this. But yeah, this is the first problem. Yeah, for this one, Serdar is writing, I think he just put the solution on Discord. Let me check. Let's see. Oh, not yet. Okay, I'll wait just a second. All right. So I'm gonna type out what we know so far. Let QC intersect BP at K. And then by Pappus's theorem, E, K, and F are collinear.
I sent the language.
Okay. Let me just type what I have so far. So let QD intersect AB at E. I'll just say define F similarly. And then, yeah, eventually we're going to use the hexagonal line lemma. Hold on just a second. Let me read what Serdar put. Okay, so QK over KP. Okay, so we want to show AF over FC equals BE over EA. Well, what was that? Oh, this is something I was doing before the session started with Stefan. Okay, so we want to show AF over FC equals BE over EA. And then once we show that AF over FC equals BE over EA, what does that show? What does that prove? Like, yeah, once we know that AF over FC equals BE over EA, what does that prove?
It proves QK over KC equals to BK over KP.
Oh, okay. So QK over KC is BK over KP, and that means that these are parallel. I see how it goes. Okay. So, we want to show that, I'll just write the proof backwards. We want to show that QB is parallel to PC, and that's true if and only if QK over KC equals BK over KP. That's the same as saying that AF over FC is equal to BE over EA. And then we do the calculation that you put earlier on Discord. So let me see if I can just take another look at it. So if AE equals AF equals X, so yeah, I'll just write out the methodology actually, because yeah, this might just be a calculation, but if AE equals AF equals X, so FC and BE, let me see how you got that. So FC, so we get AD, and we solve for X in terms of B and C. And then, okay, so I'll just write out the methodology here. So I'll just say let AB equal C, BC equal A, and AE equal AF equal X. Equal X. Oh. And compute then basically BE is equal to C minus X, and CF is equal to B minus X. And basically we can calculate, we have AB is equal to, is it root 3 AE, because this is X over 2. And we can compute AD in terms of B and C, and then the problem gets solved. In terms of B and C, it eventually solves the problem. All right, I'm gonna move on to another one. Well, not really. It eventually shows that the above ratio equality, which implies QB is parallel PC, and then we use the orthogonal line lemma. Okay, so right, by the orthogonal line lemma on AQ, AB, AC, and AP, We get AK and AM are isogonal. So once we know that these are parallel, then obviously AM is parallel. So yeah. Yeah, so this implies AK is its median. This is an interesting solution. A little bit of calculation. So I will move on to the next problem. Let's see.